So this is an overview of the peripheral circuits design for the subarray design up to the whole memory system. So here we are going to discuss some generic issues regarding the memory design. And first we will talk about the subarray and the peripheral circuitry used in the subarray. And we have already discussed some of those in the previous lectures, like the SRAM, DRAM. And here we are going to have some generalization to other emerging non-volatile memories as well. And then we'll talk about the memory bank organization. And finally, we will introduce this NVSync simulator, which is a simulator to perform the design space for the emerging non-volatile memories. And you are going to use that to do your homework. All right, so this is one subarray for the memory and the generic peripheral circuitry. And we have discussed some of those in the previous lectures. Regardless of the memory types, you will have the array of the memory cells, and most of the memories will be a two-dimensional array. Of course, for the 3D NAND flash, then you have the 3D array. But most of the other memories are the two-dimensional arrays, and you have the word length as a row, bit length as a column. And then at the edge of the array, then we may have those peripheral circuits in the yellow color. For example, on the row side, we will have the row decoder to decode the address to the individual word length. And then before the signal arrives the word line, we need to use this word line driver to drive the long wire along the word line, because the word line will have significant parasitic capacitance. And then we have to use some drivers to basically drive the node capacitance to meet the certain timing requirement. And then on the column side, some of the circuits, some of the memories may have the pre-charge and equalization, as we see in the SRAM, because you have the bit line and bit line bar, and also we have the DRAM case as well. So on the other side, then we may have the bit line marks. So this marks, the first stage marks, is to share the sense amplifier among multiple columns. For example, here you may have like 4 columns, share one sense amp. Then you need a marks to select which column to sense at this cycle. And then after the sense amp, we may have another set of marks. For example, if you do the prefetch, right? So you can sense multiple bits at the same time. For example, here you have like 8 sense amps, for example. Then you can sense 8 bits at the same time. But your I/O, for example, in this example, you just need 1 bit from this array, this subarray. Then you need another marks to select which bit from the sense amp. After the sense amp, you may have some local register or latch to temporarily store the data. And then you will select which bit to burst out at this cycle. So you may need another marks. And then here, of course, as the edge, we may need the output driver if you want to drive this bit out to the upper level interconnect. Then you may need another driver. And you know driver is inverter, right? So a CMOS inverter will drive the signal with capacitive loading, like your wires. So here is the generic peripheral circuits for the subarray. And we are going to discuss some of the circuits in more details at the transistor level. So first, the decoder. Okay, so this is standard CMOS logic stuff. And the job of the decoder is to decode the address. For example, if you have like a n-bit address, and then you decode this to 2 to the power n output. So if this is a row address, then you have the 2 to the power n word length in the subarray. So you will do the decoding. And also for the colon, you can have the m bit for the address, and then you will decode that to the 2 to the power m colons or colon groups, depending whether you will have this bitline max or not. If you have the bitline max, then you may decode just a group of the colons as one address, one colon address, if you don't differentiate that. So anyway, so here the decoder from the logic representation point of view, then this is like the symbol, right? So this is just a very simple example for the 2-bit. So you have 2-bit input, and of course you have the inversion of the signal or the complementary signal. If you have 1 and you have the 0, or let's say you have the A1, you will have A1 bar. So then you need the complementary signal as input. And then if you have those like 4 AND gate, then you will have the 4 word line as output. And if you want to implement into the transistor, of course you can do the standard CMOS logic synthesis. But if you want to save the count of the transistors, here are some more compact design. For example, here, the first example here, this is like a static logic. The PMOS pull-up network is replaced by a single PMOS node, and this is always on in this case. And then the pull-down network is your NMOS logic, this AND gate, and no gate actually, and then you need an inverter, make it like AND. So then here, this is like a static logic, but in this case, you will consume the static leakage. In this case, if you don't do the full PMOS network. You know, if you do the full PMOS network, you have a PMOS like pull up like this, right? If you do the full CMOS logic. And then the other design is like dynamic logic. So dynamic logic, then you have the PMOS pre-charge, like a circuit, and then you will have clock to control that, and then you pre-charge the output node, and then you have the clock in for the input side. Then you will discharge according to the address bits. So this is like a dynamic logic mode. If you want to save the transistor count for the decoder, of course you can use the standard logic, CMOS logic synthesis for the standard design for this one. I will skip the details. I assume this is not the content for this course. This is your VLSI course content. But I just want to point out the decoder. Typically, you may have to do the 2-stage decoder when your address bit is none. How long is none? Typically, if your address bit is larger than 6 bits, you may need to divide the decoding into 2 stages. The reason is that if you do actually 5 to 6 bits, if you do a single stage decoding like this, of course this is an example of 2 bits. It's very simple, so the fine-in is 2 bits. But if you have 5 or 6 bit address, if you still do this single stage decoding, that means your fine-in will be 5 or 6 bits, which is not good, right? According to your CMOS logic design rule from the VLSI circuits courses. So then you may have to do the 2-stage decoding. And then for this is example for a 4-bit to 16 decoding, and we need to divide that into 2 steps. So the first stage is the 2 to 4 decoding. So here you have the 4-bit input, and then you first only do a 2-bit to 4-bit decoding. So you have some groups, and you only do the first stage decoding. This is also called pre-decoder. And then after that, then you do another 2 to 4 decoding. Then eventually you have the 4 to 16 decoding. So you need to do that. And typically in our memories, because our array size is large, like 64. 64 it means you have 6-bit already. 128, 7-bit. 256, 8-bit. Or even 1000 by 1000, like 10-bit by 10-bit. Then definitely you need to use 2-stage decoder to do that. And then after the decoder, for example, here you have 3-bit to 8 decoding, and after that, then you will have this individual, for example, 8 rows or 8 word lines. Before you drive this word line, you may have your memory cells there. This might be a long word line, right? So depending on the pitch of the word line, maybe tens of nanometer, and you may have hundreds of word lines, and hundreds of colons, bit lines. So the length of the word lines may be like a few micrometer to 10 micrometer. So the wire will introduce significant capacitance, the parasitic capacitance. So this is like a load to the word line driver. So we may need to use some inverters to drive those capacitance if you want to reach certain delay. Then you have to use some drivers to drive those capacitive load. So after the word line decoder, you will have the word line driver. And driver, is inverter, CMOS inverter. So here let's look at some examples of the driver. This is also the content of your VLSI courses. And here, if you want to drive a capacitive load, you can design a stages of inverters or chain of the inverters. And if you want to optimize the latency, then you have an optimize the number of stages. So in this example, let's assume this 1 means the minimal sized CMOS inverter, like W over L equals to 1 in certain technology nodes. And then here those numbers means the corresponding area of those inverters. For example, 4 means W over L, equivalently like 4. So here, and the last number, this number means the cap value. This number means the W over L, or the area. So here we want to drive a very large cap, unit cap. So this cap 4096 is normalized to an individual, like if you have inverter to drive like a 1 small cap, this is like 1 unit cap. But now this cap is very large because you have a long wire after this. If you lump all those parasitic cap into this node, you have like 4096 unit cap. So if you want to drive this, if you review your VLSI courses, then the number of stages and the inverter sizing has some optimized value. This is calculated by your logic effort. And if you recall your VLSI courses, you may have this concept, logic effort. So this is to achieve the minimal delay. And in this example, then here, if you have those like 1, 4, 16, 64, 56, and 10, 24, like 6 stages, then you will achieve the minimal delay, which is about 30 units, 30 RC units in the delay. And the minimal transistor will give you 1 RC unit delay if you have a minimal size inverter, and then a minimal unit cap give you 1 RC delay unit. And here, if you do this, you will get 30 unit RC delay. And if you add those area up, then you may spend a lot of unit area. Like equivalently, you need 1,000, 300, like 1,365 unit area of the CMOS inverter. So this is, of course, very large area, but you achieve very small delay. This is latency optimized. Of course, if you drive like SRAM, then you may choose latency optimized design. But for other memories, like the NAND flash and some emerging number type memory, because the latency is slow anyway, then you want to optimize for the area, for the density, or cost. Then you can just have like 2 stages. If you do 2 stages, you can calculate the delay. In this case, will be like 130 unit RC delay. The total area is just those 2, like 64 units area. So you see the trade-off between the RC delay and the unit area. And then, of course, if you want some balanced design between the latency and the area, then you can choose some other designs in between. And in this example, if you have only those 4 stages, you have like 80 unit RC delay, and then the total area will be 85 unit area. So you may have different designs depending on your optimization goals, or the metrics, or the specification of your memory. In general, for like SRAM cache design, you want to optimize for the latency. DRAM also you want some latency optimized. But for other long-term memory and flash, then you may consider more on the area. Okay, any questions so far? And then bitline marks. At the end of the bitline, then you may select which column to the sensamp. For example, here you share those 4 columns with sensamp. And in this case, you have bitline and bitline bar. Probably it's more like a SRAM. And no matter what, here there are 2 kinds of bitline marks. The first one is pre-decoder based. So in this case, you need the column decoder here. This is a simple example. You have 2 bits to 4. You have 4 columns here. 2 bits to 4 column decoder. So this decoder design will be similar as the row decoder. This is column decoder. So after the column decoder, you have 4 outputs in this case. Those 4 outputs will control some pass gate transistor, or sometimes transmission gate. You know, transmission gate is a pair of pass gates. Oops. One is NMOS, one is PMOS. Right, this is a transmission gate. So basically, those outputs will control those. Of course, you need an inverter to invert the signal to the PMOS side. So you need to have those pass gates to select which column to pass, depending on the output of the decoder. So this is one type, and this is more often used, I would say. And the other type is like tree-based. So in this case, you directly use a transistor tree. For example, in this case, you have 4 pass gates controlled by the address 1 and then address 0, then of those you need to have 2 of those to control that. So it's like a tree, but this is not preferred if your address bit is none, because if you have more stages and it's a more number of bits, then the signal will pass more stages of the pass gate, so you introduce more delays in the colon sensing. So it's preferred to have this colon decoder. Okay, so I assume that you have some pre-knowledge from the VLSI courses. So here you will understand better about those circuits. Those are standard CMOS circuits. And then we will introduce the bitline RC model. So here, if we model the memory cell, no matter which memory, you can always model the memory cell as this dash box here. So the memory will introduce some current, memory cell current, and also the memory will have some resistance from the outside. If you look into the memory cell, it's like your like a Leveling or Norton like equivalent circuit, if you recall your undergrad circuit theory. So look into the memory cell, you will have some output current, I, and you will see some like output impedance, in this case some resistance, Rm. And then the bitline here, this is your bitline, and bitline will have the, actually if you want to model it correctly, because the bitline is none, you have to do a distributed RC network. It's more like your transmission line, if you recall your circuit theory. So you have those segments of the RC. So R is like your R wire, the wire resistance, and C is your parasitic capacitance per segment of the wire. So you have those many RC components. It's like a distributed RC network. And at the end of the column, then you have your sense amp. And sense amp, you can also model it, in this case, as a load to the bitline. So then look into the sense amp, you will have the RL as a load, which is the input impedance of your sense amp. And here, let's say the RT is the total wire resistance. So you have the small segments. If you add them up, you will have R total, RT. And you have those distributed capacitance. If you add up, you will have the total capacitance, CT. So here we have an equation. And we don't want to go into the tedious derivation, but this is a conclusion. So if you look at the delay, if you have a signal, for example, your current signal coming out from the memory cell, you want to know the delay when it reaches to the sense amp here. So you will have some delay, delta t, when the signal propagates from here to here. According to the transmission line theory, this is how it looks like, the delta t. Depends on those parameters. RT-CT is the total wire resistance and total wire parasitic capacitance. And also the Rm is the memory cell resistance. And RL is the load resistance from the sense amp. So this is a complicated equation. And next, we're going to simplify that. Consider two cases. The first case is the voltage sensing. If your sense amplifier is going to sense the voltage from the bitline, what does that mean? If you sense the voltage here, this is the end of the bit line. If you sense the voltage, so if you sense the voltage, the sense amplifier equivalently should have an infinite input resistance to the sense amp, which means the RL as a load to the bit line will be infinity. Ideally, your voltage mode sense amplifier will have open circuit as the end. Right, because you sense the voltage here, you don't want current flow here, you just want to have open circuit here and then have a probe here to monitor the voltage. So this is like open circuit. So if you have open circuit, RL goes to infinity. So from this equation, you can see if RL goes to infinity, so this term inside the bracket, what would be the value? Infinity divided, basically this goes to infinity and other terms do not matter. So it's like infinity divided by infinity. It's like what? What? 1, right? Mathematically. So then similarly here, this is also 1. Then this is much simplified. If this is 1, this is 1, then you will get the delta T like this for the voltage sensing. Voltage sensing. And next, we show another case, which is current sensing. Current sensing means what? So here you want to read out the current from the bit line. So if you want to read out the current, this is current sense amp. Ideally, if you want to read out current, this RL should go to 0. You have a short circuit load because you want to read the accurate current. You don't want the resistance from your sense amp to interfere with the current from the bit line. Because if you have some resistance here, then your current will be different from the bit line, right? But what you want to sense is the real current from the bit line. So ideally, your RL should go to 0. This means short circuit as a node. If RL goes to 0, right? So you can do the derivation by yourself. So you get rid of those terms and then you rearrange. Eventually you will get this equation. This is for the current sensing. The delta T, the delay from here, the current propagated from here to here. So you have those two equations. Actually, oh, I think there's some typo. I should. Let me update that after class. The two equations, I think I copy and paste wrong. So they are different. They are different. So let me update that next time. You have a different equation other than this one. I think I just copy paste those two slides. I forgot to change this one. Anyway, so you can do it by yourself. You get rid of the RL and then you rearrange the terms. It will become some simpler formula here, other than this one. Okay, so let's look at some examples. Which one is faster, current or voltage sensing? And this is taken from a very old paper, like 1991, JSSC, for the S run. Those are the parameters from this particular paper for some old technology node. So in this particular case, the memory cell resistance give you 2,500 ohm, and the total wire resistance in this case is 250 ohm, and the total capacitance is 2 picofarad. As I said, this is some old paper, so those capacitance value is pretty large for the wires. But for today's design, typically the capacitance should be in the range of femtofarad, tens of femtofarad, because the technology scaled. But anyway, if you use those parameters, the 3 parameters, and use the equations like this one, you can calculate the approximate delay for the voltage sensing and also current sensing using the other equation. But if you do that, here are the numbers. For the voltage sensing, it's slower, like 5 nanoseconds, and for the current sensing, it's like 0.2 nanoseconds. Again, this is an older technology node, like 30 years ago. But this gives you some qualitative understanding of the voltage mode and current mode. And generally, current mode will be faster in most cases. Of course, there are some cases voltage mode may be faster, but in general, current mode could be faster. This really depends on the memory cell resistance and your RC parameters of the wire, depending on the array size. Those RT and RCT depends on the technology node, depend on the array size, like your 64 by 64 or 1000 by 1000, then the RT and CT will be different. All right, any questions here? Next, we will spend more time on the sense amplifier. This is the most critical component in the peripheral circuits. And also this is the most component that have the variations, different designs. So because the decoder and the driver and the mux, those are pretty standard CMOS logic. You don't have too many variations of those designs. If you look at different memory cells, different memory arrays, they look pretty similar. You don't have too much choices. And for the sense amplifier, actually this is most innovation happens even today. If you are hired as a memory circuit design engineer in the companies, then you spend the most of effort here on the sense amplifier, because those depend on specific technology and your design targets. Okay, so let's look at some of the simple sense amplifier. And this one is a very simple one, this sense amplifier. And here we have the example of the S1. But no matter what, you can think the other memories as well. You can have, even for other memory, you only have 1 bit line, like DRAM, or other like emergent number type memories, you only have 1 bit line. The sense amplifier always like differential input. You have one input from your memory bit line. The other input will come from some reference or dummy column. So you need some reference as another input to the sense amplifier. It's always differential input. You need some reference. So SRAM provides you the reference naturally because it has bit line bar. But the other memories, like the DRAM, as we discussed before, right? You only have 1 bit line. Then where does the other bit line come from? For example, in the open bit line architecture, as we discussed before. right? You have to borrow the other bitline from the other subarray, for example. So you always need the differential inputs. And this is the simplest voltage mode sense amplifier you can think of. This may not be a good one for this advanced technology node, but this is the simplest sense amplifier you can think of. So voltage mode, okay. So you have the bitline and bitline bar, or bitline or the reference. You can think the bitline bar is the reference. So you have those two inputs from those two long wire. From those bitline, you may go through the marks before that. But anyway, you have those two inputs. And then this is like a differential pair, right? You have two NMOS. And then bottom you have the current source, provide the current to those two branches. And this is controlled by the sense amp enable signal. And then for the single-ended output, what you can do is to have a current mirror. This is PMOS, to basically mirror the signal back to here, or you basically convert the current to here. For example, if this current goes down, this current will go up, differential input, and this is mirrored here, actually go up as well. So you can amplify the output. The output will be the difference between the pull down and pull up current strength. That will change the voltage here, or the output voltage. And then here the output voltage, if you drive another like inverter, then the inverter VTC curve, you can pull it up and pull it down, then you will get 1 and 0 out. So this is the simplest voltage mode sense amplifier. Why is this voltage mode? Any idea? Why is this voltage mode? Because the signal goes to the gate of this transistor. And the gate, you know, in the DC mode, you should not pass current through the gate, right? The gate is MOS. So, as we just discussed, it's like an open circuit, right? From the input side. If you look into the gate from the bitline, you will see a very large like input impedance from the gate. So this is like you sense the voltage, because the gate will carry that voltage. Gate will not conduct the current. Of course, you will have the transient current goes on and off there. But from the DC point of view, the input to the gate of the transistor will give you the voltage sense. And then this is the timing waveform. I will skip that. It's pretty straightforward. So basically, for the voltage mode sensing, what you will do is to pre-charge the bitline bar. So here you have bitline and bitline bar, or the reference. And this will have the parasitic cap, as we discussed earlier. So you pre-charge and let them decay depending on the current through the memory cell. If the current through the memory cell is large, then you will decay faster. The other side reference will decay slower, or it will not decay at all. So then you will create the voltage difference between the bitline and the bitline bar. So once you create large enough delta V, then you turn on this sense amp enable. After you turn on the sense amp enable, then here this circuit will work, right? Depending on the input voltage difference, it will flip and the output will flip. So this is how you get the data out. So this is a very straightforward process. Any questions? And another improved design, if you want to have a faster operation, you can use this latch-based voltage sense amplifier. So here, actually, you have seen this before. This in the SRAM cell. So this is not like another SRAM, right? But maybe here sensor enable, and sometimes we have the PMOS here as well, right? As a complementary next signal to control the PMOS. So basically, in this case, this is a latch, and then you have the voltage, 2 voltage here. Before the sensor sample enabled, then this latch is floating, right? Floating, then those 2 nodes can be the same potential depending on your pre-charge or equalizer circuit, as we discussed before. So those 2 nodes can be the same initially, and then depending on the memory cell, in this example S1, right, you have charge, and the other one you don't have discharge, for example. Then this one will decay, this one will stay. Then after you create this delta V between those 2 nodes, then you turn on this sense sample enable. So this latch will flip, as we discussed before. So then you will get the output. Because this is a positive feedback, so this is pretty fast in terms of flipping time here. So typically latch-based sense sample can give you fast flipping time. At least this flipping time can be fast. I'm not talking about the signal propagation time from here to here. So this one still depends on the delta T, as we discussed before. Here I'm talking about the flipping time is when the signal reach here, and the final stage is to turn on the sense sample enable. After you turn on this, those 2 will flip to the 1 and 0, and that flipping time is pretty fast in this case. So there are 2 delays actually. One, if you think about this, first is the signal develop time, this delta T, right? It depends on how fast the signal propagates from here to here. You develop the delta V. And after that, you turn on the sense sample, and then you will flip. So the second flipping time, this flipping time, T flip, is pretty short, because you have positive feedback there. And next, we are going to show some more complicated designs, and you can read more details from this review paper. It's a pretty good paper. And this is used for the emerging non-volatile memory, next sensing, next 1T1R cell, as we discussed before. This R can be R1 phase changing memory or your M1 magnetic memory. Basically, you have this 1T1R based colon, and then here you will have this like voltage mode sensing. And in this case, because the 1T1R will decay to the ground, so in this particular example, if you look at this, it's a PMOS pair, PMOS differential input pair, and then you have a PMOS current source attached to the VDD. So this is a PMOS version of the differential pair. And then the load to the PMOS is this NMOS region. And the NMOS region actually, as we discussed earlier, if you want to flip fast, you can use a latch here as a load. Here, this is 4 transistor is a latch. This is like a load to flip. So in this example here, what you will do is to pre-charge, again, pre-charge this bit line through this pre-charge signal. You can pre-charge here and pre-charge here to the, for example, your VDD. And then depending on the memory cell you select, for example, the select one will, this is unselected, so the word line will be grounded. So there's no current flow here. There's no current flow for this cell. But then for this selected word line, this one should not be grounded, I should say. This one should be turned on, actually. So this cell, depending on the high and low resistance, you will have large current or small current. Then here the voltage decay can be slow or can be fast. If you have large current, then you will decay this voltage faster. And then again, you create this delta V after some time, delta T. And after that, this voltage is already lower than the other reference. You have a negative delta V here. And then you turn on the sense sampling enable. Then this latch will start flipping, and then you will get the output depending on the decay speed. You will need a reference here in the middle for those two cases. For example, if you sense the low resistance state, then current is large, you will decay faster. If you sense the high resistance state, current is small, then you will decay very slowly. So after some time, you get this delta V. But if you place your V reference this side, it's a constant voltage somewhere in the middle, then you can differentiate those two voltage at this moment when you turn on the sense sampling enable. This is voltage mode. And then this is the current mode. Okay. Similarly, we sense the array, like 1T1R, and this should be turned on. So you have a reference column. And the reference column, actually the RL should be in the middle. Should somewhere in the middle. This resistance, you should provide be in the middle of the high and low resistance states. So you want to use that as a reference. So here, then you will, let's say, this will be off. So here, depending on the resistance high and low, you will have different current flow here. This current is the read current from the cell. This is one branch, so the same current. Oops. So here you have another mirror. This mirror will mirror the current here. And similarly, from the reference side, you have current here, and you have a mirror. And actually here, this is a trick. So if you cannot get the resistance in the middle, for example, in the M run, you only have two states. You cannot get the middle resistance. What you can do is still you can use the low resistance state here. But here from the current mirror, you can play some trick. Because here the ratio is 2 to 1, the W over L. So this current will be half down to this side. So equivalently, like you have a like half of the current from the reference cell. So anyway, you have those two currents, and those two currents will charge those two loads in different speed. Then these two loads will have different voltage, high and low, and then through this inverter, you will flip the inverter high and low as the output. So here, this is current mode. The reason is that here we always transfer the current. The current goes to the source, for example, for the P3 transistor, and then copy the current to the P1. And then the P1 current will go to the N1. So here always the signal is going to the source or the drain of the transistor. And this is the current, right? Because current flow from drain to source for the NMOS. So you always play with the current in this case. So this is a current mode sensing. And here are some timing diagram for the circuit. And again, we have to wait for the current to flow. And then depending on the high and low resistance state, we have two different current profile. And then the reference is a dashed line in the middle. The other side For example, if you half down the current from the LRS, you will have the half current as a dash line in the middle. So this can be a reference from the other side. And then the output will be flipped after we turn on the sensamp enable signal here. So as a summary, for the voltage mode sensing, your signal should go to your gate, typically. And as a current mode sensing, your signal will go to your source or go to the drain of the transistor. All right, so this paper also compare the voltage mode versus current mode in different settings, depending on the low resistance state, the low resistance state resistance, the LRS resistance, and also the array size. The number of cells per bit line, let's say 16 up to 1,000 cells along the bit line. And you see here, this is from the SPICE simulation. And here, for example, let's look at this triangle symbol. Triangle symbol means the low resistance state is 10 kilo ohm. If your cell resistance is 10 kilo ohm, then you have those two branches, and you see that for the let's see, for the larger array size, like your 512 or 1000, which is here, and then the red ones are the current mode. So the current mode is faster. This is a delay, normalized delay. So you see the current mode is faster for the large array, especially here when the high resistance state, the low resistance state becomes higher, like 100 kilo ohm, then the break-even point even move to here. So above like 128 by 128 array size, then you see the current mode is faster. So generally, the conclusion is that for larger array, and the smaller current to sense, then the current mode faster. This is generally true. And here is a survey of the sense amplifier sensing delay for different technology, like the NAND flash, NOR flash, and the R1. So here, depending on the rate cell current, and we know that NOR flash, you have a large current flow, relatively speaking. Typically, the readout current is like tens of microamp. And NAND flash is pretty more current. Here, this is like NAND flash. NAND flash, we have a string of those transistors, and the current is very small, typically hundreds of nanoamp. That's why the NOR flash you can sense in tens of nanoseconds, and NAND flash you have to sense like tens of microseconds. So this is a general trade-off, but if you design the circuit smartly, you can also push the sensing to this range. This is a small cell current, like hundreds nanoamp, but you can get tens of nanosecond speed for this. I believe this is for the R1. So through this is, if you want to know the tricks, you can read those papers, because typically you have to do some switch cap and do some sampling in the circuit. It's a very advanced technique. I will not go into that in this course, but if you are interested, you can read those following papers. There are different kinds of techniques to improve the sensing speed using the different kinds of techniques. Like the sampling is one typical method. Sampling means that you have some switch capacitor to sample the voltage or the current from bit line, and then you decouple that from the bit line, and then you have local sensing from the sampling capacitor to the sense amplifier. I will not go into the details. And also another challenge in most of the sense amplifier design is to overcome the process variation or the offset of the sense amp. This is typically sense amp, as we discussed, right? You can think this is a differential amplifier. And ideally, those two inputs will not have bias. Those two inputs should be treated equal. But due to the process variation, right, so one input may become stronger than the other one naturally, right? So this means there is a built-in, if it's voltage mode sense amp, that means there is a built-in offset. For example, if you think about the two transistors as a differential pair, right? I draw it good, but you know this is like one input, this is another input for the voltage mode. If you have a VTH mismatch, right, so one is always stronger than the other one. That means this one, the signal needs to be larger than this delta offset to make it flip. So this delta offset will shrink your sense margin. Previously, you have the delta V from the bit line decay, right? Your bit line decay, you have this delta V. And this delta V needs to be larger than this delta offset because you don't want the process variation to overwhelm your delta V. So there are many research and innovations ongoing for the sense amplifier design. Okay, any questions? All right, we have time, so let's move on. So here, let's talk about some higher level organization. So this is very generic. And if you think the three levels we talk about here, the bank level, and in different technology, you may have different names. You may call it bank, you may call it block. So it depends. But here, let's make it generic. We assume that here we have like those. Actually, you can forget about the block. So let's say you have three levels: subarray, mat, and bank, from lower level to higher level. And then you have those like hierarchical design in the memory, right? So here the green one is one bank, and one bank you have many of those mats, and from those mats, within the mat you have many like subarray. So this is always the hierarchy. In some cases, in some memories, you may only have two levels of the hierarchy. In some cases, you may have four levels. Depends. So here are the questions. How do you want to size those subarrays or size those mats, those small units? You have different options, right? For example, if this is a subarray, for the same total amount of capacity, so here you can think those are number of bits. In those two cases, the total number of bits are the same, but you can organize that into different fashions. So on the left-hand side, you can have larger subarray, but less number of subarray. In this case, just four. And in other case, you can break up that into more smaller subarray, So what would be the trade-off? Intuitively speaking, you can imagine this one, right, will be more area efficient, but slower access. That's a larger delay. Why is that? Any idea? So why this one is less area efficient? Oh, sorry, more area efficient. Let's see. So from the area point of view, so here you can see that the memory cell area is the same, the red region, the area, right? Because as we said, the total number of bits are the same. So the red part, if you add them up, they're the same in terms of the area. What is different is the peripheral circuit, right? Because at the edge of the array, we have those peripheral circuits. So for the right-hand side, you will have more of those peripheral circuits because you need them for each, and then you need to add them up, or you need to communicate between. So you will have more of those inter-array peripheral circuits. And also even for from the decoder point of view, even from the decoder, right? So if you have like like for example, this is large decoder. Let's say like a 10-bit decoder. And then here you have like a 5-bit decoder. Then this is not proportional, let's say. So if you do the 10-bit together, it will be more compact than you do multiple of those like 5 bits together, separately. So here, generally, if you have a larger subarray, you can reuse or share more of those peripheral circuits. So the peripheral circuits area will be smaller. So that's why from the total arrays perspective, you will have less area. That means area efficient. But then the left-hand side will have slower access. Why is that? Any idea? Yes. So one simple reason could be the wire RC delay, right? For example, this memory's larger subarray, right? You have your driver here, and then you have to drive a long wire. So the RC delay will be longer than this one. So generally, if you have larger array size, then you have slower access. So that's why if you look at the array size, typically for the SRAM, as we discussed, you have even 32 by 32 for the L1 cache, like kilobit level. And then maybe L2, L3, you have like a 64, 128. At most 256 for the SRAM. And DRAM generally you have like a 512 or even 1000. And NAND flash, if you recall, of course the number of word one string is limited by the string length like 64, 128. But number of bit length along the same column or the page size can be like 8 kilo, 16 kilo, or even 32 kilo. So in the NAND flash, you have much larger subarray size, or in the NAND flash they call block size. So you generally see those trade-off between different kinds of memories, depending on the trade-off, again, between the area and the speed or the latency. And then here, you can also think about how to activate those subarray. For example, when you fetch the data, you can design the controller should specify which subarray to fetch the data. In this particular case, we are going to activate two, this is activate mat per row, activate mat per column. So here you are going to activate those from those 2 by 2, like those four, in this case they call format. You will fetch the data from those formats. And then within the mat, you're going to here have 2 and 1. Means you're going to fetch the data from those 2 subarrays. So those can be changed by your architectural level design, depending on the I/O requirement, how many data you need to prefetch. So those are the design variables. If you are a higher level designer, right? Let's say if you have a computer architect, then you need to design higher level organization. So those are the issues you need to address. So here, let's look at some of the sensing scheme at a higher level. So here, for example, we have multiple subarray, and each subarray have its own sense amplifier. And then the local sensing means that you can sense the signals locally at each subarray. And then here we use H-tree routing to accumulate the bit. For example, if you get 1 bit from one array, you need to accumulate those 8 bits to your I/O, right? So this is your I/O. So you combine those 8 bits here. So how? Here you can use H-tree. H-tree is always like this H shape. And if you want to do more, then you will. So this is like your root. This is like your leaf. I mean, it's a tree, right? So here, sense amplifier can be placed locally, and then you have full swing signal. That means you already convert to 1 and 0 locally, and then just get those 8 bits out shown in this animation. So this is H-tree routing, more like a bus-like channel. And then the other design could be global sensing. That means if you want to save the area, you can share those sense amplifier at the edge. You don't need to have that individually. Then you will have the signal, the partial swing signal. That means analog signal, like your delta V or delta I, going through the routing. So here, those are the delta V or delta I. And then the sensing happened at higher level. So in this case, then you can save some spaces. You can share the sense amp between subarrays. This is another possible design. But in this case, you have to deal with delta V, those analog voltage going through the interconnect routing. So let's have one example, real example, to look at some of those design considerations. So this is taken from the SanDisk paper back in 2014. They reported a 32 gigabit R1 chip. This is a resistive random access memory in 24 nanometer technology node. And here, this actually is like a 3D point array, but with R1 instead of phase change memory as used in Intel or Micron. So here the R1 is also equipped with some selector, and we don't know the details. They didn't disclose. And if you look at the cross-sectional view, so this part is a cross-point, 2-layer cross-point, the shared bit line and 2-word line. And then this is this part, and the half pitch is 24 nanometer, so here it's pretty small. And this is on top of those peripheral circuits. You could see the transistor here pretty large. So I would say that CMOS peripheral circuits in this design probably in like 130 or 180 nanometer. and they didn't disclose. But if you look at the pitch here, here is very small, like 24 nanometer. This is disclosed. But then if you look at those transistors, it would be large. But anyway, so this is the table for the summary. The total chip has 32 gigabits, and the total die size 130 millimeter square. And interface is like LAN compatible. Page size is 2 kilobytes. Read latency is pretty slow, 40 microseconds. Write latency is also slow. It's NAND, more like a LAN speed. And we can look into the design later, figure out why this is so slow. It's the R1 technology. At the cell level should be pretty fast, but the overall latency is pretty slow because of the design. So here let's visit the R1 organization. And in total 32 gigabits, and then it is distributed into 16 bays. They call bay. You can think bank. You can have different names. Doesn't matter. This is the highest level of the division or partition. 32 gigabits into 16. That means each bay is like 2 gigabits. And then if you look into one bay, then you have those like 32 blocks along the road side, and 4 stripes along the corner side. So basically 32 by 4, like a subarray. In total, like 128 subarray. And here are some images under the microscope. And then I will skip the details, but this is like overview. And then within one block, this is the specification. So within one block, actually it's a pretty large block. In this case, later you can figure out why this is so slow. So you look at the array size. 2K word bit length. If you think about the array, like 2. I should not draw this way because it's a 3D X point like. So let's say you have many 2K bit length, and then 4K word length, and then you have those 2 tier. So that means you have the same thing like this. Oops. And 2 layer. Right. So this is like one block, one cross point, like this one. Cross point. Let me look at the time. And I want to. Oops. So let me quickly go over this. So here just some dimensions, and then each bay here has only 64 sense amp. So that means each this only have 64 sense amp. So here only 64 bits can be accessed simultaneously because we only have 64 sense amp at the bay level or bank level. And then the page size is 2 kilobytes. So you need to have multiple times of the read or the write operations because every time you only get 64 bits, but your I/O interface is like 2 kilobytes for the one page. So you need to spend a lot of time. And the sensing is at higher level, it's not locally. So the sense amplifier is shared between multiple arrays. And I think we will discuss more details later, maybe next lecture, for the details of this sensing. And but I want to point out here, the sense amplifier is shared among multiple blocks. So you have this non-H tree routing in this case. So due to the time limit, so let's stop here, and we will continue from here next lecture.